All right, Chem 111, this is practice exam 5, our last exam for the semester. So let's get going here. It's first question. The number of lone electron pairs in the nitrogen molecule is, well, if we look at nitrogen and we tally up the total number of valence electrons, nitrogen has 5 valence electrons. So if we have 5 multiplied by 2, that gives us a total of 10 valence electrons. And I'm not going to reteach Lewis structures, but basically you end up with a triple bond between the two nitrogens like that. And so the total number of lone pairs is 1, 2. And so the answer is we have 2 lone pairs in the nitrogen molecule. Next question, which one of the following compounds uses both ionic and covalent bonding? Well, the first one is aluminum sulfate. And if we think about aluminum sulfate, aluminum is a metal, isn't it? It's a metal. And the sulfate anion is completely made of nonmetals, right? Both sulfur and oxygen are nonmetals. So if we think about this, we're going to have the aluminum ion. We're going to have 2 of these. These are aluminum 3+, right? Aluminum is always 3+. And then we have 3 sulfates. It's SO4 2-, SO4 2-, and SO4 2-, like that. And so since we have, again, we have metals and nonmetals interacting via their charges, that means that this compound has ionic bonding, doesn't it? And if we look at the structure of the sulfate anion, so if we draw the Lewis structure of the sulfate anion, and it's not asking us to do that, but I'm just going to go ahead and draw it here. So we have a negative charge on this oxygen and this oxygen. Well, the bonding that's in, the sulfate anion is all covalent bonding. And so aluminum sulfate has both ionic and covalent bonding. If I look at CO2, for example, carbon dioxide has only covalent bonding, right? Because carbon dioxide is made completely from nonmetals. The same rationale would apply with the carbonate, right? Carbon and oxygen are both nonmetals. And so I'm just drawing the Lewis structure of the carbonate ion quickly here. But again, you can see it's completely metals and nonmetals. Magnesium chloride, that's composed of magnesium 2+, which is a metal, and 2 chloride ions, which are nonmetals, and so that would be ionic. And then the last one is C6H12O6. You might recognize that if you've studied biology before. That is the sucrose. That's the molecular formula for glucose, rather. And so even if you didn't know that, glucose is comprised completely of nonmetals. And so this would be a covalent compound as well. So we have covalent, ionic, we have covalent here, and then we have covalent there as well. All right. The next question, number 3, the covalent bond with the greatest polarity would form in which of the atom pairs below? So if we're looking for the greatest polarity, we're looking for the biggest difference. So largest difference in electronegativity. We have carbon oxygen, boron oxygen, sulfur oxygen, bromine bromine, and carbon phosphorus. Well, I'm just going to reproduce some of the periodic table here quickly, just for us to work with here. There we go. All right, so we have all the elements that we need here. So if we look at A, it's the difference between carbon and oxygen. But remember that electronegativity increases as we go in this direction and in this direction. This is an increase in electronegativity, and this is an increase in electronegativity. Right? Fluorine is the most electronegative element on the periodic table. Well, if I compare just the first 2, you can automatically see that boron and oxygen are going to have a greater difference in electronegativity than carbon and oxygen will. If I look at sulfur and oxygen, well, they're in the same group or family. So they're not going to have a very big difference in electronegativity. If I look at bromine and bromine, well, there's going to be no difference in electronegativity there. So that's definitely not polar. That's completely nonpolar. And then if I look at carbon and phosphorus like that, you can see that the difference in electronegativity between those is not going to be as great as boron and oxygen. So that's going to be the most polar bond out of all of these. Now, I don't expect you to memorize all of the electronegativity values, but if in case you're interested and in case you are able to memorize most of these, The electronegativity of oxygen is 3.5, and that of boron is 2. And so we get a delta En of 1.5 for the boron-oxygen bond. And if you compare all the others, you'll see that none of them are as great as 1.5. All right, but again, you can solve this one completely qualitatively just by following the trends on the periodic table, the trend for electronegativity. All right, number 4, it says classify the carbon-chlorine bond in carbon tetrachloride as ionic, polar covalent, or non-polar covalent. Well, if we do the same thing here, if we draw our periodic table, and I'm just reproducing a little bit of the periodic table. Well, one of the ways that you can memorize electronegativities is most students have fluorine memorized, that it's 4. As you go backwards, it drops by a half. So you go from 4 to 3.5, 3, 2.5, 2, like that. So that means that carbon is going to be 2.5. There's another quick and dirty rule, which is the down 1 and over 2 rule. Let me show you what I mean. If you look at nitrogen, which has an electronegativity of 3, if you go down 1 and over 1, 2, chlorine will have something close to 3. It'll be in the vicinity of 3. Even if you don't have it memorized, that's neither here nor there. But you can see that the difference in electronegativity will roughly be 3 minus 2.5, which is 0.5, right? Our cutoff was around 0.4, so this is definitely a polar covalent bond. Not only is it polar, but we know that it's covalent because the bond is between 2 nonmetals, and so this is a polar covalent bond. Question number 5, the Lewis dot symbol for a calcium ion. Well, if you look at calcium on the periodic table, it's element number 20. Calcium is in group 2A. And so if I was to write the Lewis structure for calcium, just calcium by itself, it would be calcium with 2 dots like that. And if you're wondering, hey, Mr. Deon, could I put the dots like this? I don't care. It doesn't matter. I like them on the sides like this. But remember, when we have a calcium ion, in order for calcium to become isoelectronic with the closest noble gas, which would be argon, it has to lose 2 electrons. And so it becomes calcium 2+, and we lose 2 electrons. And so the Lewis dot symbol for calcium 2+ is simply calcium 2+. We don't have any electrons surrounding it, right? It's lost its 2 valence electrons. And remember that Lewis dot symbols only include valence electrons. For example, if you think of fluorine, fluorine is in group 7. So we have 1, 2, 3, 4, 5, 6, 7. Okay, so we only include valence electrons, and the calcium ion has no valence electrons. It's lost them in order for, again, it to be isoelectronic with the nearest noble gas, which would be argon. Question number 6. Which of the elements below would most likely form a polar covalent bond when bonded to oxygen? Well, remember that oxygen has an electronegativity of 3.5. Anyhow, we're looking for a polar covalent bond. If oxygen is bound to an oxygen atom, right, what's that going to look like? That's going to give us an O2 molecule. Now, that's going to be completely nonpolar because there's no difference in electronegativity between 2 oxygens. I'm going to go over this one kind of quickly, and you should notice that sodium, magnesium, and aluminum all have something in common, right? These are all metals. And since oxygen is a non-metal, that means that when oxygen is bonded to sodium, magnesium, or aluminum, it's going to form an ionic bond, okay? Whereas when oxygen is bonded to hydrogen, like you see in water or in alcohol, and I'm just kind of isolating or, kind of just highlighting that oxygen-hydrogen bond. Well, hydrogen has an electronegativity of 2.1, and oxygen has an electronegativity of 3.5. And so the difference is 1.4. Now, that's neither here nor there. But again, the hydrogen atom bound to an oxygen is the only possibility here that would be considered a polar covalent bond. Number 7, the number of lone electron pairs for the perchlorate ion, ClO4- is, well, they're asking us here to draw a Lewis structure, aren't they? Let's tally up the total number of electrons. We have perchlorate ion, which is ClO4 minus. Chlorine is in group 7. It's got 7 valence electrons. Oxygen is in group 6. It's got 6 valence electrons. 6 times 4 is 24. 24 plus 7. And then we add 1. And we get a total of 32 electrons. And so I have my 32 valence electrons. Chlorine is going to be my central atom. Remember, a rule that we learned is that oftentimes, most of the time, the least electronegative element will be in the center. So again, I'm not going to reteach Lewis structures this evening, but if we draw the Lewis structure for the perchlorate ion, it looks something like this. Chlorine is in the 3rd period and can expand its octet. And so here's our perchlorate ion. Let me just fix that 1 electron here. And so what's the total number of electron pairs? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. 9 electron pairs in the perchlorate ion. Number 8. Which of the following is a useful guideline for the application of formal charges in neutral molecules? For example, if you think of something like water. Water is a neutral molecule, right? And here's its Lewis structure. Anyhow, let's take a look at the possible answers. It says A, a Lewis structure in which there's no formal charges is preferred. Well, that's not necessarily true. The B, the preferred Lewis structure is one in which the positive formal charges are on the most electronegative atoms. Well, that's definitely not true because you would want the negative charges on the more electronegative atoms. Sorry, I misspoke. In A, it says a Lewis structure in which there are no formal charges is preferred. Okay. Yeah, so that's definitely true. Lewis structures with large formal charges +2 +3 are preferred. That's not true. Okay, anyhow. Yeah, so the answer, a Lewis structure in which there are no formal charges is preferred. Yes, absolutely, right? We can draw a Lewis structure where we have formal charges, but when we have no formal charges, that's going to be preferred in a neutral molecule. Okay, let's take a look at the next one. It says, which of these solids is going to have the lowest melting point? Notice they all have something in common. They're all ionic compounds comprised of potassium and a halogen. So they have fluorine, chlorine, bromine, and iodine. We're talking about the lowest melting point, okay? So lowest melting point means that it's going to have the weakest. We're looking for which one of these is going to have the weakest intermolecular forces. Well, these are all ionic compounds, okay? These are all ionic compounds. Well, how do we rank the strength of an ionic bond? It's based off of the electrostatic interaction between the cation and the anion. Remember that the energy, the strength of the bond is going to be proportional to the charge on the cation or the product of the charge on the cation and anion divided by the radius. All right, so that means that the bigger the charge is, okay, the bigger the numerator, the higher the energy is going to be. But you see that each one of these has a charge of +1 and -1, +1, -1, +1, -1, +1, +1, -1. So we can't solve this problem by examining the numerator. We have to go to the denominator and look at the radius or size. Okay, so remember, large charges are going to make a stronger bond, and smaller, okay, radius is going to make a stronger bond. Sorry, thinking backwards. Sorry, you guys. A larger radius. Okay, let me go over this again. So, the larger charges are going to result in a higher energy, and the smallest, sorry, I'm looking for the lowest melting. I don't know why I keep thinking the strongest one. I can't stop thinking about the strongest bond. Anyhow, we're looking for the weakest bond, okay? So if I'm looking for the weakest bond, I'm going to want to have the largest radius. Sorry. All right, so if we think about the size of the halogens, right? Size increases like this. So we'll put here large and small, like that. So since iodine is the largest of all of them, the one with the lowest melting point or the weakest intermolecular forces is going to be potassium iodide. All right, now that I finally have stronger bonds out of my brain. Okay, let's take a look at question number 10. It's about carbonic acid, acid that's found in soft drinks. Carbonic acid is a weak acid that contributes to the taste and produces the carbon dioxide bubbles in all carbonated beverages. How many valence electrons are used to show the Lewis structure for carbonic acid? Well, you could either tally up all the valence electrons that are shown in here, or you could just use the formula H2CO3, which I think is easier. Hydrogen has one valence electron. It's in group 1. There's 2 hydrogens. Carbon is in group 4. It has 4 valence electrons. And oxygen is in group 6. It has 6 valence electrons. So that's 18 plus 4 is 22 plus 2. And that gives me a total of 24 electrons. That's one way. If you wanted to tally them up by looking at the bonds in the lone pairs, you would go like this. You'd say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Either way, you end up with 24 valence electrons in carbon dioxide. Question 11, assuming the octet rule is obeyed, how many covalent bonds will an oxygen atom form to give a formal charge of 0? This is one of those rules that I think is handy to memorize. And this is something that I went over with you, is that oxygen almost always has 2 bonds, and 2 lone pairs. And if you're like, well, where would I see that? Let me give you some examples. What about the oxygen in a water molecule? It's got 2 bonds and 2 lone pairs. What about the oxygen in carbon dioxide? It's got, both of those oxygens have 2 bonds and 2 lone pairs. What about if I drew this molecule? This is formaldehyde, and we looked at the orbital overlap diagram for formaldehyde. What do all of these oxygens have in common? They all have 2 bonds and 2 lone pairs. And so the answer is 2 will be the number of covalent bonds that oxygen will form when it has a formal charge of 0. Another way you could approach this problem or think about this problem is that oxygen is in group 6, and so it has a Lewis dot structure that looks like this. You have 2 unpaired electrons, so it's ready to form 2 bonds. Number 12, this goes back to one of the first questions we looked at, if not the first question of this practice exam. It says, list all types of bonding present in the compound calcium carbonate. Well, if we think about this, we've got a calcium, which is a metal, right? Calcium is a metal. And then you have carbonate, which is comprised completely of nonmetals. And so this compound, nonmetals, this compound definitely has ionic bonding, doesn't it? Between the calcium ion and the carbonate ion, like that. So it's definitely got ionic bonds in it. But if we examine the carbonate ion, which is comprised completely of nonmetals, and we draw its Lewis structure, it looks something like this. Well, since the carbonate ion is made completely of nonmetals, it's got covalent bonding. Well, is it polar or is it nonpolar? There's a difference in electronegativity between carbon and oxygen, isn't there? If you look at the periodic table, boron, carbon, nitrogen, oxygen, fluorine, right? This is the first period. You can clearly see there is a difference in electronegativity between carbon and oxygen. In fact, the delta En is around 1. 2.5 for carbon and 3.5 for oxygen. So that's a polar covalent bond. And therefore the answer is C. It has both 1 and 2. It has both ionic and polar covalent bonding in calcium carbonate. Number 13, which one of these polar covalent compounds would have the greatest percent ionic character? Well, the greatest percent ionic character is going to be related to the largest difference in electronegativity. Notice that each one of these compounds contains hydrogen. So we don't even have to know the electronegativity value for hydrogen, do we? Because we know that if we look at the 4 halogens, fluorine, chlorine, bromine, and iodine, we know that electronegativity increases in this direction. And so the most electronegative of the halogens, in fact, the most electronegative element in the periodic table is fluorine. And so the greatest difference in electronegativity is going to be found in HF, and so it's going to have the greatest or most percent ionic character. BeF42 minus is called the fluoroberylate ion. The formal charge on the beryllium atom ion is, or beryllium atom in this ion is, well, let's come up with a Lewis structure. We've got BeF42 minus. Beryllium is found in group 2A. It's got 2 valence electrons. Fluorine has 7 valence electrons times 4. That's 28. And then I get 2 more from the 2 minus charge. So that's 28 plus 4. That gives me 32 valence electrons. Well, if there's one rule I hope you remember with making Lewis structures, it's about fluorine. When you have fluorine, fluorine can only ever exist in one way. Only ever have 1 bond and 3 lone pairs. 1 bond and 3 lone pairs. No exceptions to that. Therefore, just based off of that, we know that our compound has to look something like this. It's going to have beryllium, and it's going to be surrounded by 1, 2, 3, 4 fluorines like that. And then we're going to fill them all up with their octets like this. Well, here I have 8 total valence electrons, right? 3 lone pairs and 2 electrons in the sigma bond. 8 times 4 gives me 32. And so I've used up all of my electrons. All of the fluorines are identical. If you calculate the formal charge on a fluorine, fluorine has 7 valence electrons minus 1, 2, 3, 4, 5, 6 dots and 1 stick. Okay, remember my magic formula? That gives you a formal charge of 0. So none of those fluorines have any charge. But if I look at the beryllium atom, beryllium has 2 valence electrons. Beryllium is the 4th element in the periodic table. It is found in group 2A. 2 valence electrons minus 4 sticks minus 0 dots. Wow, that gives me -2. And so the 2 minus charge is found on the beryllium atom. So we'll put 2 minus there, like that. Number 15 deals with resonance structures. Notice if you look at my solutions, there was something screwy in here that I should have fixed when I made this slide presentation, but I'm just going to scratch out the parts. So the whole thing about obeying the octet rule, yeah, that's not important because this doesn't obey the octet rule. And if you're like, why would that be? Well, chlorine is in the 3rd period, and remember that once you get into the 3rd period, elements can expand their octets. Also, you can clearly see from this Lewis structure that chlorine exceeds the octet rule. Okay, well, it says here, here's a beautiful Lewis structure for the chlorate ion, showing all non-zero formal charges, positive charge on the chlorine, negative charge on the oxygen, and it's asking us how many resonance structures for the chlorate ion are possible. Well, remember that this double-headed arrow like this is a resonance arrow. Okay. And the way this Lewis structure is drawn, it looks like we get a single bond here, a single bond here, and a double bond here. But we know that because of resonance structures, that's not really true, is it? We know that it's kind of like each one of these chlorine oxygen bonds is kind of like 1 1/3 of a bond, right? Because this double bond is here, here, and here, right? But in order for us to represent that, we have to draw the Lewis structures or the resonance structures. So the way we would draw that is we would show the double bond being on the top, okay, like this, like that. And we would also show the double bond being on the left-hand side, like this. And there we go. Those are all the possible resonance structures. So the total number of resonance structures is 1, 2, 3. Question number 16. Which one of the following is most likely to be an ionic compound? Remember that ionic compound, so ionic is formed from a metal and a non-metal. Remember that covalent compounds are formed from non-metals only. Non-metals, like that. If I look at ammonia, sulfur trioxide, chlorine trifluoride, and phosphorus trifluoride, these are all non-metals. Everything in here is a non-metal, right? Iron, on the other hand, is a metal, right? And chlorine is a non-metal. And so the only compound here that's going to be ionic would be iron 3 chloride or ferric chloride. Either way you want to name it is fine by me. Okay, number 17. How many covalent bonds will be drawn to phosphorus in the phosphate ion for the dot structure that expands the octet in order to minimize formal charge, and if necessary, places negative formal charges on the most electronegative atoms? That's just a lot of, fancy speak for saying, draw the Lewis structure of the phosphate anion. Well, let's start by tallying up the total number of valence electrons. So if we have PO43 minus, phosphorus has 5 valence electrons, oxygen has 6 times 4, and then we add 3, so that's going to be 24 plus 8. That gives us a total of 32 valence electrons. Our phosphorus is going to be in the middle like this, surrounded by 1, 2, 3, 4 oxygens. We still haven't used up all of our electrons, but when you finish up the Lewis structure, it's going to look something like this, where you have negative charges. The 3 negative charges are all going to be on oxygen atoms because oxygen is much more electronegative than phosphorus. And so here's our Lewis structure. It's asking us how many covalent bonds are there drawn to the phosphorus. Well, we have a total of 1, 2, 3, 4, 5. And so the answer is there are 5 covalent bonds drawn to the phosphorus in the phosphate ion. Next question, which of the following Lewis structures is incorrect? If you look at the first one, it's ammonia. So this is ammonia, and there's nothing wrong with this Lewis structure. All 3 of the hydrogens have a duet because they're in group 1A, or sorry, they're in the first period. And nitrogen has an octet. If you look at the next ones, you can't really see the bond, but it's supposed to be there. Okay, it's supposed to be just a fluorine molecule. So that's good. If you look at this one here, though, we have Houston, we have a problem, don't we? All right, you can see that the nitrogens have an octet, but if I was to calculate the formal charge on this nitrogen right here, nitrogen has 5 valence electrons, subtract 4 dots and 2 sticks. That would mean that both of these nitrogens have a charge of -1. So we get a problem there. Another problem is that you have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 valence electrons shown here. Nitrogen only has 5 valence electrons, so N2 should have a total of 10 valence electrons. And the Lewis structure would look like this. And so this is the one that's going to be incorrect. The next one is hydronium. So this is hydronium, the hydronium ion shown here. This is H3O plus, and that's perfectly fine. And the next one is methane. This is just methane, and we looked at the structure of methane, and everything is copacetic there. Okay, well, let's move on from there. Question number 19. How many resonance structures can be drawn for the phosphate ion? We already drew one Lewis structure for the phosphate ion, and it looked something like this, where we had the 3 oxygens bearing, each one bearing a -1 charge like this. Okay, and then we had 1 oxygen that has no formal charge. The phosphorus is in group 5. It's surrounded by 5 sticks and 0 dots. That gives me a formal charge of 0, so everything looks good there. Now, if you look at this resonance structure, if you look at this Lewis structure rather, you'd say, okay, well, there's a double bond here. We know that that's not true, right? Lewis structures are just our best way of, one of the best ways we have of representing the structures of molecules or ions. And we know that these electrons here in that pi bond, they're not localized between this, the phosphorus, and that oxygen specifically. Rather, those 2 electrons are delocalized. How do we draw them being delocalized? Well, we're going to show the double bond as being on the left, like that. We're going to show the double bond as being at the top, like this. And then we're going to show the double bond as being over on the right as well. And so all 3 of these extra resonance structures are perfectly reasonable. And when you add up 3 plus 1, you can see where I'm going, but I don't want to leave improper or incomplete Lewis structures in my video. I go, negative, negative. There we go, like that. And so the total number of Lewis structures, or resonance structures that we can draw is 4. Question number 19. List all the types of bonding present in the S8 molecule. Not an easy question. Okay, this is one that you might have to fiddle with a little bit. But if you think about it, I mean, even if you were unable to draw the Lewis structure, if it only contains sulfur, and the sulfur is bonded to another sulfur and another somehow, there's no difference in electronegativity between two sulfurs. And so this is really just nothing more than a conceptual question. Okay, it's impossible for there to be a polar covalent or an ionic bond here. And so the only answer would be non-polar covalent, or E. Now, if you were able to come up with a Lewis structure for S8, it looks something like this. You draw all the sulfurs at the 8, vertices of a stop sign like this. And sulfur is like oxygen. It always has 2 bonds and 2 lone pairs. So this would be the Lewis structure of S8. But again, you don't even have to come up with that, right? Since all of the atoms are identical, there's no way that you could have any polar or ionic bonding in this molecule. Question 21, which one of the following molecules has a central atom with an sp2 hybridization? Well, we could spend some time drawing all of the Lewis structures here. If we look at N2O, so dinitrogen oxide, its Lewis structure looks something like this, and we drew its Lewis structure earlier on in the class. If I look at sulfur dioxide, it's got a Lewis structure that looks like this. Okay, something like that. I'm kind of drawing these a little bit quick, but anyhow, there we go. Phosphorus pentafluoride looks something like this. And I guess I'll put the lone pairs in. This fluorine always has 1 bond and 3 lone pairs, no exceptions to that one. The next one is nitrogen trifluoride, which looks like this. We could draw and show the molecular geometry. It's trigonal pyramidal. And the last one is beryllium chloride, which looks like this, BeCl2. It's a linear molecule like that. Well, if I look at the hybridization of each one of these, there was a table that we looked at in the very last chapter, chapter 10, which enables us to identify quickly the hybridization. Now, this nitrogen is only bound to 2 atoms, and so it is sp hybridized. Sulfur dioxide, it's got 2 bonds and 1 lone pair, and so it is sp2 hybridized. The phosphorus and phosphorus pentafluoride is surrounded by 5 fluorines, and so it's sp3d hybridized. The nitrogen and nitrogen trifluoride, 3 bonds, 1 lone pair, it's sp3, and then the beryllium here is sp hybridized. And so the answer is sulfur dioxide. Since it's surrounded by 1 lone pair and 2 atoms, it is sp2 hybridized. Question 22, ibuprofen is used as an analgesic for the relief of pain and also to help reduce fever. It's an antipyretic. What is the hybridization state of the oxygen indicated by the arrow in the structure of ibuprofen shown below? Well, you can see there's a carbon bound to an oxygen, and then there's also a hydrogen in there. So what that would look like is that I'm going to have my bond coming down from my carbon. I'm going to have my oxygen, then it's bound to a hydrogen like that. What do we know about oxygen? It always has 2 bonds and 2 lone pairs. So since that oxygen has 2 bonds and 2 lone pairs, it is sp3 hybridized. Question 23, the bond angles in the carbonate ion are expected to be, we draw the carbonate ion, and we've drawn this a couple times already this evening, so I figure you've got this one memorized by now. We know that this is just one of 3 resonance contributors, isn't it? Right? We could move this pi bond, right? We could move the negative charge, and we could put the pi bond up here. Okay, so we know that that pi bond could be anywhere. It could be here, it could be here, it could be here. And so all of these bonds are going to be equivalent, and they're going to repel each other equally. And that would result in a bond angle for all of these bonds as being 120 degrees, right? If we divide 360 by 3, we end up with 120 degrees. What's this question asking? It's making sure that you understand resonance structures, right? That you're not saying, well, hey, come on, I got a extra lone pair here and an extra one here. It's going to repel this. No, that is not the rationale. You have to understand that this is only one of 3 resonance contributors to the overall resonance hybrid. Number 24. Give the number of lone pairs around the central atom and the molecular geometry of CbR4, carbon tetrabromide. If we tally up the total number of electrons in CbR4, we got 4 from carbon, and then bromine is in group 7 times 4. So that gives me 28 plus 4, so that gives me 32 total electrons. Carbon is the less electronegative element, so it's going to be in this, it's going to be in the center, and it's going to be surrounded by 1, 2, 3, 4 bromines. So carbon's octet is already filled, and for the bromines, they each are going to need to have, sorry, I can't see. They're each going to need to have 3 lone pairs around them like that. And so there's our Lewis structure. There's nothing wrong with that Lewis structure at all. But in order for us to determine the molecular geometry, since we have 4 groups of atoms and no lone pairs, the arrangement is going to be tetrahedral, won't it? We're going to have 2 bromines in the plane of the screen like that, a bromine going back, and a bromine coming out like this. So this shows my molecular geometry. Remember, all of these bond angles are 109.5 degrees. And the molecular geometry of that central atom, that carbon, is tetrahedral. It's got no lone pairs around it, and so the answer is 0 lone pairs, and it is tetrahedral. Number 25, the number of pi bonds in the oxalate ion is, well, the first thing we need to do is draw the oxalate ion. If we tally up the total number of electrons or valence electrons in the oxalate ion, carbon has 4 times 2, that's 8, plus 6 times 4, that's 24. 24 is 8, 32. We add 2 more, and that gives us 36 valence electrons like that. Well, in the interest of time, I'll just go ahead and I'll draw the Lewis structure of the oxalate ion, which is the conjugate base of oxalic acid. And it looks something like this, where we have 2 negative charges on oxygens, which are going to be trans to each other or on opposite sides of the double bond due to repulsion. And so remember that when we have a double bond, that the first bond in any double bond, right?
Mr. Deon?
Yes.
I think our total number of electrons is actually only going to be 32 instead of 36.
24. No, I think it's 34. So it's 8 plus 24 plus 2. Yeah, it's 34. There we go. All right. We tally them all up. Look, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Okay, so the answer is 34. We have a total of 34 valence electrons. Sorry, we didn't tally that up correctly, but remember that every bond, the first bond between 2 elements, is called a sigma bond, right? All of these bonds, that's a sigma bond, this is a sigma, right? This is a sigma, this is a sigma, but remember the second bond is always called a pi bond, okay? And I could circle whichever one of these bonds I want, but here is a pi bond and here is another pi bond. So that's a total of 2 pi bonds. And so the answer is we got 2 pi bonds in the oxalate ion. Question 26, which of the following substances is or are bent? Let's draw some Lewis structures here. Showing molecular geometries, we got H2S, hydrogen sulfide. So we have H2S, which is going to be bent. We've spent some time looking at H2S, which is similar in structure to H2O. So it is bent. If we look at carbon dioxide, CO2 is a linear molecule. We actually looked at its structure earlier on today, so linear. If we look at ClNO, I'm not going to go over the whole thing here from soup to nuts, but if we have ClNO, it looks something like this, or we're going to have a single bond to chlorine. Oops, let me draw it down like this. A single bond to chlorine, and the chlorine has 3 lone pairs, and we're going to have an oxygen like this, and then we'll have a lone pair like this. And so you can clearly see that the molecular geometry here will be bent. What else do we have? We have the, this is called the amide ion, NH2 minus is called amide. Anyhow, that nitrogen is going to have 2 hydrogen atoms. It's got a negative charge, so it's going to have 1 lone pair in the back and another lone pair coming out in the front. Right, the electron geometry is tetrahedral, but the molecular geometry is going to be bent. And then finally, we have the ozone. And ozone looks something like this. And you can draw the lone pair like that, or you can draw it at the end of a line like that. Whatever you find helpful is good, you know, whatever works for you. But the ozone ion, or the ozone molecule rather, looks like this. Okay, so you can see that it is also bent. And so the ones that are bent are H2S, oops, no, not CO2. So those 4, so everything except for CO2, is that one of the answers? Yeah, here we go. Okie doke, let's move on to question 27. A molecule with 3 single bonds and 0 lone pairs of electrons is predicted to have which type of molecular geometry? If it's got 3 single bonds and 0 lone pairs, it's got this form, AB3. So that means it's a central atom surrounded by 1, 2, 3 atoms, and those 3 atoms are going to seek to get as far away from each other as possible, and they're all going to adopt bond angles of 120 degrees, which means the molecular geometry and the electron geometry would be trigonal planar. Question 28 says, predict the geometry and polarity of the CS2 molecule, carbon disulfide. Well, an easy way to remember this one is if we draw some of the periodic table over here. This. We've got carbon and sulfur. Well, sulfur is right next to what? It's right next to oxygen. Everybody by now, hopefully, has the Lewis structure of carbon dioxide memorized. So carbon disulfide is going to be the same. It's going to be CS2, 2 double bonds like that, right? The carbon is surrounded by 2 regions of electron density. And so it is linear, okay? And if we think about the polarity, well, there is a dipole, right? Because there's a slight difference in electronegativity between carbon and sulfur. I know I taught you the down 1 and over 2 rule, but even if there was or there wasn't a slight difference, it wouldn't matter, because since the molecule is linear, even if these were polar bonds, doesn't matter if they're polar or not, because if they aren't polar, then the molecule is nonpolar, and if they are polar, they cancel out. And so this molecule is linear and nonpolar. So whatever small dipole is here is canceled. Number 29. According to valence shell electron pair repulsion theory, the molecular geometry of ammonia is, well, everybody should know what ammonia is. It's NH3, and it has a Lewis structure and molecular geometry that look like this, or I'm going to have 1 hydrogen in back and another one coming up in front like this. And remember, molecular geometry considers bonds only, okay? Where are the bonds? I've got a bond going down here, here, and here. And so that is trigonal pyramidal. Trigonal pyramidal. Here we go. Number 30. Consider the dichlorine with a positive charge, chlorine, and chlorine with a negative charge. So it's a chlorine cat. I should say it like this: a chlorine cation, a chlorine molecule, and a chlorine anion. That's the best way to say it. Which of these species is paramagnetic? Now, keep in mind that chlorine is in group 3. Okay, chlorine is in the third period. Period 3. If you look at the handout that I'm going to provide to you, it shows you the molecular orbital diagrams for, I have it here somewhere with me, Okay, it gives you the molecular orbital diagram for lithium. Let's write it down here. It gives you from dilithium to nitrogen, and then it gives you another molecular orbital diagram for oxygen to dineon. Okay, now since chlorine is a halogen, right? Chlorine, even though it's in the third period, right? These are all second period elements here, but the molecular orbital diagram that you're going to use is going to fall under here, right? Because oxygen, O2 to Ne2, what's in the middle there? What's missing, right? It goes O2 and then F2 like this. And so Cl2 would be right underneath it. And so you're going to use this MO diagram. Okay, that's the one you're going to use to solve this problem. Now, I'm only going to consider valence electrons to solve this problem. So that's all of the electrons from the third period. What is the electron configuration of chlorine? It's neon, and the valence electrons are 3s2, 3p5. That means it's got 7 valence electrons. Okay, so that means that in Cl2 is going to have 7 times 2. It's going to have 14 valence electrons. Cl2 with a positive 1 charge, I remove an electron, so it's going to have 13 electrons. And Cl2 with a negative charge, I add an electron, so it's got 15 valence electrons like that. Okay, so now that I've got all of that information in mind, I'm going to move some things around here to make a little space for myself. And I'm going to draw the molecular orbital diagram here on this slide. So we're going to start with a sigma 3s, then we're going to have an anti-bonding or sigma star 3s. We're going to have a sigma 3px. We're going to have a pi 3py, a pi 3pz, a pi star 3py, a pi star, remember the stars are anti-bonding, 3pz, and then a sigma star 3px. This is the way the book does it. Okay, this is the way our textbook does it. Now you'll notice that on my handout, it's a little different. Okay, you can see the labeling of the orbitals is a tiny bit different, but they're in the exact same order. Okay, so what are we going to do? Why don't we start with, we'll start with chlorine. Okay, it's got a total of 14 valence electrons. Why don't we put it in red? Okay, so we're going to do Cl2 first. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. No unpaired electrons. Okay, it's asking us which one of these is paramagnetic. In order for something to be paramagnetic, it's got to have unpaired electrons. Must have unpaired electrons. And so Cl2 is diamagnetic like that. If I want to do Cl2 plus, okay, let me remove all these electrons. There we go. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I've got an unpaired electron right there. So this is going to be paramagnetic. If I do the Cl2 minus, try again. So I'm going to erase everything here. Let's put them in. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15. I've got an unpaired electron, and so it is also diamagnetic. The answer is the two species that are, did I say diamagnetic when I meant paramagnetic? Sorry. It's got an unpaired electron, so it is paramagnetic. Oops. Paramagnetic. Okay. So the two that are paramagnetic are going to be Cl2 plus and Cl2 minus. Like that. Give me a thumbs up if you follow me on that one. Just need to catch my breath here. Stop thinking so quickly. All right, thanks, Bruce. All right, perfect. Okay, well, let's move on. Question number 31. Good, thanks, Ishi. Good to see my students are here. Number 31, a nonpolar covalent bond, for example, or what it means by that is pure covalent, would form in which one of the following pairs of atoms? Well, if it's purely covalent, that means there can be no difference in electronegativity. Could anybody answer this one for me? Stretch. Which one of these would have no difference? Trevor says B. I couldn't agree with you more, Trevor. Right? How could there be a difference in electronegativity between two atoms that are identical? Right? So that's purely covalent. All right. If I look at, C, that's a metal and a non-metal. That's going to be ionic. This is going to be ionic. This is going to be polar covalent. And then if I have selenium and bromine, there's going to be a difference in electronegativity there. It's not very big, so it's probably non-polar covalent. But either way, it's not purely covalent. The only one would be Br2. Perfect. Great. Thanks for the answer. Number 32. Which one of the following compounds does not follow the octet rule? This is just another, example of needing to draw some Lewis structures. You can see that in Br2 or the bromine molecule, the octet rule is followed there. In carbon dioxide, anything that's in the second period has to follow the octet rule, and both carbon and oxygen are in the second period, so there's no way that could fall outside of the octet rule. The same thing follows for carbon tetrafluoride. It would be literally impossible for that to break the octet rule because all of those elements are in the second period. In order for the octet rule to be broken, you have to have an element from the third period or beyond. You look at nitrogen trifluoride, exact same thing, right? Every element is from the second period, like that. Oh, sorry, I thought the question said exceed the octet rule. It says does not follow the octet rule. Okay, well, you can see that NO does not follow the octet rule. Why? Because nitrogen has a total of 5 valence electrons and oxygen has a total of 6 valence electrons, so that equals 11 valence electrons. And I think that we looked at the Lewis structure of nitrogen monoxide, which looks like this, and we actually have an unpaired electron. So unpaired electron. And so that nitrogen does not follow the octet rule. Sorry, first I thought it said exceeds the octet rule. Doesn't obey the octet rule. Let's see, number 33. What's the charge on a phosphorus in the Lewis structure for the phosphate ion that satisfies the octet rule? Well, we looked at the Lewis structure of phosphate earlier on this evening, didn't we? I drew it at least once, and it looked something like this. Remember that phosphate, right, you should know is PO4 3 minus. So that means that 3 of the oxygens, 1, 2, 3, are going to have negative charges, but this does not obey the octet rule, does it? All of the oxygens in this obey the octet rule. I promise you they all do. But the phosphorus is surrounded by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So that does not obey the octet rule. How would I make that obey the octet rule? What I'd have to do is I'd have to move the 2 electrons from that pi bond and put them on top of the oxygen like this. So I'd end up with a structure or a Lewis structure that looks like this. So now I'm going to have a negative charge here, a negative charge here, a negative charge here, and a negative charge here. So that structure does obey the octet rule, but you're saying, well, now you've got 4 minus charge. I thought the charge on a phosphate was 3 minus, and it absolutely is. So that means there must be a formal charge on my phosphorus. Phosphorus has 5 valence electrons. Subtract 4 sticks and 0 dots gives us +1. And so there is a positive 1 charge on the phosphorus, and that is the answer. Question 34. What's the formal charge on the oxygen atom in N2O? Dinitrogen monoxide. And it also shows us the order that the atoms are going to be in the structure of this molecule? Well, if you tally up the number of valence electrons in N2O, we've got 5 for each nitrogen, so that's 5 times 2 plus 6. That gives us a total of 16 valence electrons. If I put my nitrogens together and my oxygen like this, I fill up the octet of the oxygen first. I'm gonna, put a pair of electrons here like this. I'll put another pair of electrons here like this. Nobody's octet's filled up. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And then if I put 15, 16 like that. Well, there's a problem here because the octet of this nitrogen has not been met. This nitrogen has an octet and the oxygen has an octet. So in order for me to fix that, I'm going to take this pair of electrons and I'm going to put them or share them between these two nitrogens. Now all 3 of the atoms in this Lewis structure have a complete octet, but there are some formal charges here, aren't there? This oxygen, the only oxygen, has 6 valence electrons, subtract 6 dots and 1 stick. That gives me a formal charge of -1. So I'm going to put a -1 charge there. If I look at the nitrogen in the center, nitrogen has 5 valence electrons, subtract 4 sticks and 0 dots. That gives me +1. So I'm going to put a +1 charge right there. Now, that's a neutral molecule. I want to double check to be sure that this nitrogen has no formal charge. The nitrogen has 5 valence electrons, subtract 3 sticks and 2 dots. That gives me 0. So everything looks perfect. That means the formal charge on my oxygen is -1. It also makes sense because the negative charge is on the more electronegative atom in the Lewis structure. Number 35, which one of the following molecules has an atom with an incomplete octet? Well, this is one of those kind of questions where I went over specific examples of molecules that have incomplete octets, or atoms, sorry, that will have incomplete octets. Can anybody identify which one of these compounds would have an incomplete octet? Which one of these molecules, I guess, would possess an atom with an incomplete octet? Well, if we draw some Lewis structures here then, for NF3, nitrogen trifluoride, we drew that one this evening. Every element has a complete octet. Let me push that up a little bit here. There we go. In H2O, and everybody should be able to draw the Lewis structure for H2O. You can see that the oxygen has a complete. It's kind of a maybe not a great question because the hydrogen only has a duet, doesn't it? Okay. If we look at germanium tetrahydride, same thing because germanium is in the fourth, is in group 4A. So germanium tetrahydride is going to look like this. Anyhow, the germanium has an octet, but in boron trifluoride, right? The boron is going to have 3 bonds to the fluorine. Anyhow, I think a better wording for this would be has a central atom with an incomplete octet. And so you can see that the boron is only surrounded by a total of 6 electrons. Arsenic is in group 5, and so it's going to have a Lewis structure that looks like this. There we go. Okay.